A warm welcome to everyone. Myself, I am Dr. S.M. Suresh, Assistant Professor of Physics, Erode Secondary Engineering College, Erode, Tamil Nadu. So today we are going to see about magnetic materials. So in this session we are going to see about magnetism in materials, magnetic field and induction, magnetization, magnetic permeability and susceptibility, types of magnetic materials. So first of all we have to see the origin of magnetism. So the nuclear spin and orbital motion of electrons give the magnetism. The nuclear spin gives the weak effect and orbital motion of electron gives the strong effect. Magnetization. The process of converting a non-magnetic material to a magnetic material is called magnetization. Intensity of magnetization. So it is a magnetic movement per unit volume is called as intensity of magnetization. So next one, magnetic flux. The total number of magnetic lines of force in a magnetic field is called magnetic flux. The unit of magnetic flux will be Weber. Magnetic flux density. The magnetic flux density per unit area at right angles to the direction of flux is called the magnetic flux density. The unit of magnetic flux density is Weber per meter squared. Magnetic flux intensity. It is a magnetomotive force per unit length of the magnetic circuit. It is also called magnetic field strength or magnetizing force. Magnetic permeability. It is the amount of magnetic lines of force penetrating through the material is called magnetic permeability. It is represented as mu equal to B by H, where mu is the magnetic permeability, B is the applied magnetic flux density, and H is the applied magnetic field. Relative permeability. The ratio of flux density produced in a material to the flux density produced in a vacuum by the same magnetization force is called the relative permeability. Magnetic susceptibility. The ratio of intensity of magnetization produced in the sample to the magnetic field intensity which produces magnetization. This magnetic susceptibility has no units. It is represented as psi equal to m by h, where psi is the magnetic susceptibility, m is the intensity of magnetization, and h is the applied magnetic field. So now we are going to see about types of magnetic materials. So based on the magnetization, the materials are classified into three major types. First one is diamagnetic materials, second one is paramagnetic materials, third one is ferromagnetic materials. So now we will see about this classification. So from this figure we can see the difference between these three materials. So in the first figure we can find that the diamagnetic materials does not allow any magnetic lines of force penetrating through the sample, whereas in the case of paramagnetic and ferromagnetic materials, these materials allow to pass through the magnetic lines or magnetic lines can pass through these paramagnetic and ferromagnetic materials. So the diamagnetic materials are repulsion of magnetic lines of force from the center of the material, but in the case of paramagnetic material, attraction of magnetic lines of force towards center of the material, whereas in the case of ferromagnetic material, heavy attraction of magnetic lines of force towards center of the material. The diamagnetic materials are weakly repelled by a magnet, whereas paramagnetic material is weakly attracted by a magnet, and for ferromagnetic materials, strongly attracted by a magnet. So the diamagnetic materials are weakly magnetized in opposite direction of magnetic field, but in the case of paramagnetic material, it also weakly magnetized in the same direction of magnetic field. In the case of ferromagnetic materials, it is strongly magnetized in the same direction of magnetic field. The diamagnetic materials have negative value of magnetization, and for paramagnetic material it has positive and small value, but in the case of ferromagnetic material it is a positive and large value. The diamagnetic materials lose their magnetism on removal of external magnetic field, but in the case of paramagnetic material they lose their magnetism on removal of external magnetic field, and in the case of ferromagnetic material they do not lose their magnetism on removal of external magnetic field, that is they are permanent magnets. And in diamagnetic material it has no unpaired electrons, but in the case of paramaterial it has few unpaired electrons, and for ferromagnetic material it has more number of unpaired electrons. The examples of diamagnetic materials are solid, liquid, gases, and the examples are water, copper, mercury, gold, and hydrogen, etc. The examples of paramagnetic materials are aluminum, platinum, sodium, and ground glass. The examples of ferromagnetic materials are iron, nickel, and cobalt. Curie temperature is the temperature below which a material can act as a ferromagnetic material, and above its temperature the material can act as a paramagnetic material. This behavior is called Curie temperature. Curie-Weiss law. The Curie-Weiss law describes the magnetic susceptibility psi of a ferromagnetic material at temperature above the Curie point. It is represented as psi equal to C divided by T minus Tc, where psi is the susceptibility, C is the material specific Curie constant, T is the absolute temperature, Tc is the Curie temperature in Kelvin. As the temperature increases, the magnetism of ferromagnetic materials decreases. So next we are going to see about domain theory, hysteresis, soft and hard magnetic materials, ferrites and its application, and applications of magnetic materials. So next we are going to see about domain theory. This domain theory was proposed by Weiss in 1907. So this theory is deal about ferromagnetic materials. First of all we have to consider the ferromagnetic material is divided into many domains. That is, the ferromagnetic material is separated and divided as a different many domains. So without the field, each domain have random direction, that is the direction of magnetization before the applied magnetic field, it has random direction. But when we applied the external field, each domain has the same direction as that of the external magnetic field. So in the figure B we can find that each domain has the same direction of magnetization with respect to the external magnetic field. So during this process there are three major steps are happening. First one is unmagnetized specimen for random orientation of domains. Second one is single domain process. Third one is rotation of domain along the field. So in the figure we can find that without the field, each of the four domains have the same area, but when we apply magnetic field, that is when we apply weak magnetic field, the domain which has the same direction, that is the domain which has the same direction will increase in its area compared to the other domains. And when we apply strong magnetic field, all the domains are trying to align in a direction, that is in the applied magnetic field direction, external magnetic field direction. So when we apply weak magnetic field, that domain which has same direction as that of external magnetic field will grow in its size, and when we increase when we apply strong magnetic field, all the domains are trying to align in a parallel direction with respect to that of external magnetic field direction. So the next we are going to see about the 4 energies that involved in the domain theory of ferromagnetism. So first one is exchange energy. It is the interaction energy which makes the adjacent dipoles align themselves. So from the figure, when we apply external magnetic field, each domains exchange energy and form a single domain. So it is the interaction energy which makes the adjacent dipoles align themselves together. So next one is anisotropy energy. So it is the difference between magnetization takes place in easy direction and magnetization takes place in odd direction. So from the figure we can first one corresponds to the iron in the BCC structure, second one is nickel in its FCC crystal structure, and third one is cobalt in its hexagonal crystal structure. So in the first diagram, that is in the iron BCC structure diagram, so we can find that 100 plane is the easy direction and 111 is the odd direction. But in the case of nickel, 100 plane is odd direction and 111 is the easy direction. Third one, domain wall energy. It is a transition layer or domain wall or block wall. So thick wall is due to the gradual changes in the spin, but thin wall energy is due to the abrupt change in the spin. So the anisotropy energy is directly proportional to the thickness wall leads thin wall. That is, thick wall is due to the gradual change, that is the change of spin is gradually taken, gradually considered. But in the case of thin wall, the change in spin is abruptly changes. So fourth one is magnetostrictive energy. When a ferromagnetic material is magnetized, a change in dimension of the domain is produced. The phenomena is known as magnetostriction and the energy is known as magnetostrictive energy. That is, the domains either expand or shrink. So in the first diagram, without the magnetic field, it has random orientation. But when we apply magnetic field, each domain has the same alignment and also it has some change in its shape. That is, the shape of the domain is varied when we apply magnetic field. That is, it is either expand or shrink in its size. So next we are going to see about hysteresis. So when a ferromagnetic material is taken through a cycle of magnetization, the magnetic induction and intensity of magnetization lags behind the external magnetic field intensity. So this phenomenon is called hysteresis curve. So now we are going to see about hysteresis BH curve. So this graph is plotted between intensity of magnetization and applied magnetic field. That is, the applied magnetic field H is taken in the x-axis and intensity of magnetization is taken in the y-axis. Initially, when we apply magnetic field, from intensity of magnetization also increases. That is, from in the region OA. That is, when we apply external magnetic field, intensity of magnetization also increases from O to A. So at certain point it reaches the saturation value. The saturation takes place in the point A. So above it cannot be further magnetized. That point is called saturation point. So now we are going to reduce the magnetic field. So when we reduce the magnetic field, the intensity of magnetization also will decrease. So now we are reducing the magnetic field. The curve is from A to B. So when the magnetic field is 0, applied magnetic field is 0, it still has some magnetization value in the ferromagnetic material. That is, even though the applied magnetic field is 0, it has some magnetic moment. That magnetic moment is called retentivity. So it is represented in OB. The area OB is called retentivity. So further, when we reduce the external applied magnetic field in the reverse direction, so at some point the ferromagnetic material loses completely the magnetic moment and reaches 0 at point C. So this point, that is OC, is called coercivity. So this coercivity is the when the ferromagnetic material loses completely its magnetic moment when the applied field is in the negative direction, is called coercivity. When we further reduce the magnetic field, it reaches the point D. It is also called as saturation point in the reverse direction. After that, when we increase the external magnetic field, it again increases to point DE and it form a cyclic curve. That is, when we increase the magnetic field, it again continues the DEF and it goes to the A point. So this forms a closed curve. So this curve is called hysteresis. So retentivity or residual magnetism. So this retentivity is happened at when we apply the magnetic field is H equal to 0 and the intensity of magnetization B not equal to 0. The amount of magnetic induction retained by the material even after the removal of external magnetic field intensity is known as retentivity or residual magnetism. Coercivity or coercive force. This is happened at the B equal to 0 and H not equal to 0. The amount of magnetic field intensity is applied in the reverse direction to remove the magnetic induction retained by the material. This is called coercivity. Energy product. It is the product of retentivity and coercivity. It represents the total energy stored inside the specimen. So next we are going to see about types of magnetic materials based on magnetization behavior. First one is soft magnetic materials and second one is hard magnetic materials. Soft magnetic materials. Materials which are easy to magnetize and demagnetize are called soft magnetic materials. So these materials we can easily magnetize and we can easily demagnetize, that are called as soft magnetic materials. Next one, hard magnetic materials. Materials which retain their magnetism and are difficult to demagnetize are called hard magnetic materials. That is, we can easily magnetize the hard magnetic materials, but it is hard to demagnetize the hard magnetic materials. So now we are going to see about difference between soft and hard magnetic materials. So first one is they can be easily magnetized and demagnetized, but in the case of hard magnetic materials they cannot be easily magnetized and easily demagnetized. Second one is they have high permeability, but in the case of hard magnetic material it has low permeability value. Third one is magnetic energy is stored is low in soft magnetic materials. In the case of hard magnetic materials, the magnetic energy stored is high. Fourth point, low it has low hysteresis loss, but in the case of hard magnetic material the hysteresis loss is high. The coercivity and retentivity are small in the soft magnetic materials. In the case of hard magnetic materials, the coercivity and retentivity are high. The eddy current loss is small in soft magnetic materials, whereas in the case of hard magnetic materials, the eddy current loss is high. The domain walls are easy to move in the soft magnetic materials, but in the case of hard magnetic materials, the domain walls are hard to remove. The examples of soft magnetic materials are iron, nickel, silver, steels and ferrites. The examples of hard magnetic materials are tungsten steel, cobalt steel, aluminium, etc. These soft magnetic materials are used as temporary magnets in electric motors, generators, relays, telephone receivers and etc. The hard magnetic materials are used as permanent magnets in loudspeakers and electrical measuring instruments. So further, the magnetic materials are classified based on the alignment. When it suffers the external magnetic field. Antiferromagnetic materials. If the permanent dipoles line up in anti-parallel direction, the material is called as antiferromagnetic material. And if the permanent dipoles line up in anti-parallel direction with unequal magnitude is called as ferrimagnetic material. These ferrimagnetic materials are also called as ferrites. The ferrites are nothing but it is a compounds of iron oxides. It consists of two or more kind of atoms. Generally, the ferrites are expressed as X2 plus, Fe2 3 plus, O4 2 minus. Here, X2 plus are magnesium 2 plus, zinc 2 plus, iron 2 plus, manganese 2 plus, nickel 2 plus, etc. Properties of ferrites. Ferromagnetic materials possess net magnetic moment. Above Curie temperature, it becomes paramagnetic while it behaves as ferromagnetic material below Curie temperature. The susceptibility of ferrimagnetic material is very large and positive. It is temperature dependent and is given by psi equal to T by T plus theta for T greater than Tn. Beyond nil temperature, its value decreases. Spin alignment is anti-parallel of different magnitude. Mechanically, it has pure ion character. And the ferrites have high permeability and high resistivity. The ferrites have low eddy current loss and low hysteresis loss. Next, we are going to say about application of ferrites. The ferrites are used in manufacturing permanent magnets, producing inductor coils used in telecommunication devices, and it used in magnetic films, magnetic discs and tapes, and it is used to production of ultrasonic waves and radio receivers. Thank you.